Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I'm Tom Ball, and it's my pleasure to welcome Charles Zhang here. He's a professor in the Department of Computer Science and Engineering at the Hong Kong University of Science and Technology, and his major area of work is in the area of software engineering. He's been focusing lately on debugging of concurrent systems, and is a PhD, MSc, and BSc with honors all from the University of Toronto. So
right.
Welcome, Charles.
Thank you. Thank you very much. All right, so I'd like to thank Tom first for giving me this opportunity to talk about my work. I'm very, very happy to be here, to be the home of chess, to talk about debugging concurrent programs. Very happy that Shaz came to give us some opinions. So before I start to talk about the research itself, let me just first generally introduce where I come from. There's some old friends know where I come from, but there are many new. So I come from a small university in Hong Kong. It's located right here on the shore of the ocean. It's quite small. It's got in total about 7,000 students. But it's quite specialized. So that's where I come from on the map. And my research group is called the Prism Research Group. It's basically established in 2009. I joined the university in 2008. So we're a pretty young research group. That's why we're happy to be here to learn from the experts. I have 4 PhD students in the group. So the research focus of our research group is we like program analysis, and we want to use it to help programmers develop large systems. Our current focus is concurrent systems, as Tom has already said. So we have a few major research projects. The topic of the talk today is one of them. It's deterministic replay of concurrent software. So I'll talk about that, of course, for this talk. And other than that, we also work on automatic fix of concurrency bugs. We have 2 papers there. We also work on causal analysis, or people call it predictive analysis over traces. And we have a few interesting techniques there. We also work on something much lower on program analysis itself. We have some technique that computes pointers more accurately, and we're happy that it's been adopted by SUT. And we also work on some database approach for program analysis. That's our ongoing work. Okay, so this is an overview of the type of research we do in a group. Of course, today I want to talk about a specific area that we have made a few interesting contributions to. It's called Deterministic User Level Replay of Concurrent Programs. It's a joint work with Jeff, who is also here, and together with pretty much everybody in the group. So this is something that everybody in the group has invested some amount of time. Okay. I want to give you an outline of the talk. For experts, I guess I don't have to explain what replay is, but for people who are not very familiar with replay, I want to define it in a very simple manner so that we know what we're talking about. And then I want to use a very simple example to illustrate some of the main challenges of performing user-level deterministic replay. Then I'll talk about some prior art to allow you to better understand the contribution of our techniques, and I'll talk about our techniques specifically those 3 techniques: leap, stride, and clap. So leap was presented in the FSC 10, stride in ICSI this year, and clap was presented in PLDI student research competition. So we know that probably the FSE and the ICSI probably are software engineering centric conferences. So I'd like to even more welcome the opinions in this audience on the work that we did. Then I'll make some conclusions. So to begin, I'd like to first define what do we mean by replay. First of all, when I talk about replay, in this talk, I want to talk about programs that use threads on a multi-processor platform and communicate through shared memory. So this is a kind of very common kind of threaded programs that we deal with. So I'm not talking about functional parallel programs like Haskell. So this is a shared memory, multi-threaded programs. So this is the kind of program we want to replay. So I'd like to offer a definition. I'd like to point out that this is by no means a very authoritative definition of what replay is. This is our working definition so that we can have an easier way to position our contribution. So I define it to be a technique that repeats a previously exercised execution according to some kind of diagnostic criterion. So that means that sometimes we replay the program to be able to time travel so that we can go back to any point in a program's execution and start to execute from that point. So we want to replay for full execution. In some other areas, we want to just browse the computed values of a previous execution. But we do not care how the values are computed. Okay? So in some other scenarios, we replay for getting the computed values. And a third category, which I argue that most of our replay technique will fall into, is for bug reproduction. Is for reproducing a particular failure. Okay? So these are the just to show you some different purposes or different criteria that each replay technique will try to achieve. The basic mechanism of replay, so the biggest denominator, despite the purpose, the goal of the replay technique itself, is that you always want to try to monitor the application, produce some log, and we use the log to try to reconstruct an earlier execution. So this is probably the basic mechanism for replay technique. In terms of research, replay has been active for many years. So the earliest paper we can find, we're not claiming this is the earliest paper. The earliest paper we can find is the Talks paper. Oops. I guess Microsoft is checking on me. All right, so the earliest paper we can find is the Talks paper in 1986. Okay, and we also all the way to this year's ICSI for our replay work. So it's just exemplary for showing that this research has been going on for many years. And the publication of replay work spanning many different areas, all the way from core software engineering conferences to hardware conferences like Micro or VEE. The good news is that if we conduct research in this area, we can have many different venues that we can publish papers. Well, of course, the bad news is that we have to read the papers from all these conferences first to understand the state of the art. So it has been a long, very prolonged research area, active in many different areas. So a replay technique can be implemented from these conferences. We probably can already sense that it can be implemented in hardware, such as modifying some hardware cache coherence messages, or it can be implemented in software at the user level from program instrumentation, or at the system level where we modify the virtual machine to enable logging of the low-level system events. Right? So it can be implemented in hardware, it can be implemented in software. A replay technique is called is what we call deterministic if it guarantees to reproduce an earlier run. So we call it the deterministic replay. We call it the probabilistic replay if it only tries to reproduce earlier on with the best effort, okay, with high probability. So there's just some common terminologies that we use in this area. Our focus in our research group is what I call deterministic user-level replay for bug reproduction. All right, so there are some terms here, so let me just explain it a little bit better. We like deterministic replay because we think that it helps the diagnostic process more effectively. And in addition, many sort of client analysis require deterministic replay, such as cyclic debugging, fault localization of concurrent programs, or bug classification, where we have to run the concurrent program again and again. Okay, so in that case, determinism is a very, very good thing to have. And also, we like user-level replay because we think that we believe it's very easy to use. It's very accessible. So what user-level replay is, a programmer take the replay technique and take a regular user program, instrument it or transform it, and just run it, right? So the replay is going to, the technique is going to monitor the application, produce a log, and replay it. So this would not affect any other application, and this would not require any OS level, system level, or hardware modification. So it's very easy to deploy. So we like this characteristic as well. And we like bug reproduction. We think that's probably the most common use of a replay. The reason why we replay is to try to troubleshoot, try to find bugs. And in particular, we focus on reproducing or producing the order of arrays. Right? So I'm going to illustrate that that's basically one of the major reasons for concurrency bugs. So we focus on producing an order of arrays so that programmer can have an easier time to diagnose the bug. And by saying that, we can relax on reproducing the original schedule or even the computed values. Right? So we focus on the race order and we relax on reproducing the schedule and the computed values. So this is sort of the focus of our technique.
So you can tell me if this is more appropriately asked somewhere else, but it seems like those goals are a little bit kind of against each other, right? Like if you do it in the software, there's a lot of benefits to that, but you're kind of getting into the world of the program. Like if you truly want to be deterministic, you know, it seemed to me that you need to remain outside of the world that the program lives in. So it just kind of seems like software is really good, but it kind of encourages probabilistic. Deterministic is really good, but it kind of it encourages other decisions that are made.
So yeah, I think well, I'll illustrate later that the software approaches have some problems, but it's good for producing many different concurrency bugs. It has its shortcoming, but it depends on how you define the goal.
Right? Is like because it's practical, right? I mean, deterministic. You always want deterministic, but you'll settle for probability if it's practical, right?
You have a point. So I'll illustrate later on for the challenges. Probably I can answer your question after that.
Okay. Thank you.
Okay. All right, so before I actually talk about the details of our techniques, I just want us all together to go through a replay exercise so that we can get familiar with some of the challenges and also some of the terminologies that I'm going to use later on. So our replay exercise actually is very simple. It's probably the simplest concurrent programs you will ever see. So we have two threads that both are reading from a global variable G and increment it locally and assign it back to the global variable G. Okay, so these are the two threads, and if we execute the threads following this order, meaning that we execute the entire computation of T2 after T1, we will compute 2 for the global variable G at the end. Okay? So G is 2. But if for some reason statement 4 is executed before statement 3, due to a different kind of scheduling, we'll have G equals to 1 at the end. Okay, so this is a very simple example. And I want to illustrate that. So for a concurrent program, the order of the race, or whether statement 4 is executed before statement 3 or after statement 3, is the key to deterministic replay. Right? So we have to restore a particular race order to be able to produce the same program output. Okay, so this is the sort of essence of deterministic replay, that we need to catch or need to restore the order of race, as illustrated by this example. Otherwise, the computation result would be different. All right, so let me just illustrate the solution. The first solution is a very intuitive solution, is that we can just record the order of race directly, right? So if the order is important, let's just record the order. So here, suppose that the order is that statement 4 happens before statement 3. And since we're doing user level recording, we're going to insert some instrumentation code and try to record this race order. So by inserting this instrumentation, we hope to produce a log of 4, 3, right? So the order is that 4 executed first, then followed by 3. But again, since we're doing user level instrumentation, our instrumentation code also suffers from the perturbation of the scheduling, right? So that our instrumentation code can be executed later than the other instrumentation code on T1, on thread 1. This will produce a log of 3, 4. Right? So if we use that log to replay this whole program, we know that, as shown by my earlier illustration, that we're going to produce a different result. Okay? So this is a very simple illustration of the problem with user level instrumentation. So in the common practice is we had to somehow make the instrumentation at the actual statement to execute atomically, or have to use some kind of synchronization. And for people who know about concurrent programming, we know that adding additional synchronization is really, really bad. Here, I want to illustrate another solution that solves the problem, is that we do not use any synchronization, but instead, I'm going to record the values that we read or write for each of the shared variables. Okay? So in this case, we can record that T1 reads G and the value is 0, and writes to G, the value is 1. So from these values, we can sort of reason that the first statement of T1 cannot happen after this last statement of T2, because the value is 0. Otherwise, the value would be 1. Right? So it's a very simple example to illustrate that it's possible for us to find a schedule given a thread local low store value just by searching. Right? So just make sure we find a schedule that is correct, for example, sequentially consistent. Gibbons et al. Has proved this many years ago that this problem is MPC. Okay? So we can do it, but it's an MPC problem. So let me summarize what the example trying to say is that the example shows you an order-based solution where we try to record the thread access orders. We explicitly track all the rewrite dependencies, and we can guarantee to replay the execution, but we need to use logs, a lot of them. Okay, so this is really, really bad. Or we can try the search-based solution. We can infer the rewrite dependencies through the low store values, require no use of locks, but it's an NPC problem, which means it doesn't scale. It means that we cannot always produce a reasonable schedule. So we're losing the determinism.
So help me understand why it's NP complete.
Well, it's not.
The reconstruction is NP complete.
So as I stated here, given the thread local low store value trace, like the ones that I show here, to decide if there is a schedule that's sequentially consistent is NP complete problem. So this is shown in the SIAM paper.
1, 2, 4, 3, 5, 6. That's the thing that's NP complete.
Yeah. So if you assign a schedule order, which one that execute first, if you want to assign a total order to represent a schedule for these statements, is an NPC problem. If you only have the value trace. Okay. So I illustrated order-based solution. I illustrated a search-based solution. And the prior art for user-level determinist replay is primarily order-based. Okay. And the representative techniques is called deja vu and rec play. And let me just briefly give you some information about these related work so that you can understand our contribution a little bit better. So to talk about the related work and also our contribution, I'm going to use a slightly more sophisticated example as the one here that involves two branches. And what's interesting about this example is that by only following the schedule, we can lead to evaluating both branches to be true. Okay, so that's the only schedule that we can follow. This just shows that we need to precisely reproduce the schedule to compute the same result. So this is the example we're going to use. And the first sort of representative work for user-level replay is called Deja Vu. It's developed by J.D. Choi, which is also a well-known name in concurrency work. So his proposal is very similar to the first order-based example that I gave earlier, which is simply if we can identify all the locations in the program where a shared access, a shared variable or shared object is involved in a computation, we can actually record the exact order of the threads that access or exercise these shared computations. Right? So we can record all of them in a global log. So we can record a global sequence of the thread schedule that compute the shared variable states. So in this proposal obviously works, right? But it's pretty inefficient because it involves synchronizing all the threads onto a global log. So in this simple example, to produce this log, it involves 6 global syncs. Eventually, these logs, to log into a global log, you essentially tie all the threads together using a global lock, which incurs a lot of runtime overhead. So to improve upon that, reg play is another representative approach presented in 2003 talks, is to use a Lamport clock. Right? So from distributed computing domain, we know that Lamport clock is a pretty efficient way of clocking distributed events. So we model each thread as a distributed process, and we model objects as the sources of distributed messages. Right? So if you know about Lamport's clock, this is a pretty straightforward mapping from that problem to this problem. So what they do is that they associate each thread and each synchronized object with a distinctive clock. And this is the algorithm, standard Lamport's clock algorithm for updating these counters or these clocks. So for our example, well, the details how we arrive these counters. How do we compute these counters is not important, but the technique is to associate each shared variable and each thread with a different clock, with a different counter, and at the end, each thread would maintain a local history of all the counter values for all the shared accesses to the shared variables. Okay, so in this way, the thread only we call it the local sync. So the thread only needs to synchronize the monitor or synchronize the observation or synchronize the logging if the thread involves a particular shared variable. So there's no need to synchronize across all the threads. So in this way, we call it local synchronization. So regplay involves, in this example, involves 6 local synchronizations plus 6 compare and update for updating the Lamport clock counter. So our contribution compared to the prior art is to still try to lower the logging overhead while staying deterministic. Okay, and we also want to simplify the replaying process. And let me just talk about our techniques now in detail. So I'm still going to use the same example that only following this path, this schedule, that we can produce this error. So I want to first talk about leap. Is a very simple idea that improves upon the regplay work. So the idea is very simple. Instead of associating each thread with a clock, we associate each shared variable with a sort of access vector. So as the program executes, we just record the sequence of threads that each shared variable sees during the execution. Okay, so we maintain the access vector for each of the shared variables. So here, same to regplay, we require local syncs. So each shared variable is required to synchronize against the threads that only synchronize with the threads that involved in the computation, or race against that variable. Do not need to synchronize all the threads. So it's the same as the 6 local syncs in this example. So the way to replay is to actually, you can think of these logs as stacks. And we're just going to read the logs one by one, or pop the item one by one, and use that value to direct a user-level scheduler. So our user-level scheduler can start to check if it is the thread's turn to read or write to that variable by checking the top of the stack. So in here, we just check if it's T1's turn to execute. And the next is that we check the top of the stack for Y and shows it's T2. So we switch to T2 and continue to execute. And then we continuously to check the log. And in this way, it's very simple fashion. In this way, we can, when we consume all the logs, we can guarantee that our user scheduler will follow the same execution path as the recorded run, and finally to produce this error. Okay. Yeah.
First, I have 2 questions. First, how do you identify the shared variable, like operator?
We use a static analysis prior to the run. So there's a phase of static analysis for identifying the shared variables.
Okay. Based on false positive, right?
Yeah, we do it conservatively. Yeah.
And the second thing is, the main reason why your recording phase is faster than the global is that you are basically allowing parallel recording. Is that right?
That's right. That's right. That's right. It's a very simple idea. We wonder why anybody hasn't thought of it earlier, but nevertheless, it's a state-of-the-art order-based deterministic replay technique. It's more lightweight compared to existing approaches, and we use static analysis and Bicol transformation to actually achieve all the questions that you just asked. We have a formal proof of replay correctness, which I haven't found in any of the earlier papers. We contribute the first automated tool available to the public for replay, which is very surprising. We couldn't find any other automated tool for replaying, but our tool is publicly available for download. And the weaknesses of this approach is also apparent. There are still too many synchronizations. We have 6 synchronizations, although they're local ones. And essentially, when we try to log these access vectors, we essentially eliminated all these low-level data races, even though many of them are very benign or intentional. Essentially, we're forcing a sequentially consistent execution of our program. So these are the weaknesses.
In your tool, would you do anything to try to optimize away conditionals? Like, because you talked about how you execute a statement and then do, if I should keep going, then execute next statement. Is there anything you do to try to, say, oh, I should just do the next 5 off the stack?
You mean for the replay part or for the
replay part?
For the replay part, we just execute when we reach a shared variable, we will actually check the log and to check if it's my turn to execute. So as I illustrated
each time.
Yeah.
You haven't found a need to put optimization, like different tricks in there.
Yeah, it's pretty well. In other words, it's pretty slow. Right? So we just force actually each computation we have to check the log to replay.
Yeah.
Yeah, we haven't done any optimization on it.
Thank you.
But our Uppsala paper actually does some kind of optimization on it. But I probably don't have time to talk about it. So, given all these weaknesses of Leap, we have improved upon it, and we propose to use a hybrid approach to address some of the weaknesses. So this is an approach that we require the recorder to synchronize on the writes, but not on the reads. So this is the main contribution of this technique of stride. I call it a hybrid approach because it is order-based, where we record write orders, similar, actually the same to the approach of Leap, and we match the values of reads. We record the read. Sorry, it's order-based where we have to record the write order. It's search-based where we record the values read, and we match those values with the writes during the replay. Okay, so this is a sort of a search element in the algorithm as well. And we use the write order to bound the search complexity, so we don't have this NPC problem. It's a polynomial time. Okay, so the total number of steps to search is bounded by kn, where k is number of threads, n is the total number of operations. So it's a polynomial search. So let me just give you some details of how stride works. Still the same example. First of all, the difference is that we record sort of access vector for writes only. All right? So for the variables, shared variables x and y, we record the sequence of threads on that involved in writes to these variables. At the same time, we record 2 values for each reads. Right? So So I'm going to zoom in on this particular thing later on. But right now, this is a sort of the log that produced by stride compared to leap. The write logs is identical to leap, and we have a sort of 2 values logged for each read. So we call it a double log. So let me just zoom in on this double log feature of stride. So this is actually the key contribution of stride. Is that suppose that we have different instances of writes on the same variable. So in my example, the series of writes produce sort of writing a series of prime numbers on a particular variable. And our reads actually, for example, in a recorded execution, the reads actually reads a second write, which is the value 3. As I showed you earlier, if we want to record exact order of race, we need to make sure the recorder and actually the actual operation happen atomically using lock. And I've shown you that this lock is actually a bad idea, right? We have to insert a lot of lock to do this. In stride, the big contribution is that we do not need this lock anymore. Instead, I'm going to read twice. The first read is going to read the actual value that committed by the remote write. And the second read is going to read the about, the sort of the version that when this read commits, it's going to return whatever the version the second read returns. We call this one is the bound. So how do we use those values to restore the race order? So our purpose is to sort of restore the order of race, right? So it turns out that our bound, number 4, gives us a search bound that we only need to match all the values committed by writes before the version 4. Okay, so this bounds our search. So that's why we're polynomial. And the rest is very simple. We just scan from the bound backwards and find the match by the value, because we have the value of reads recorded. So if you, it's very apparent that it's possible that we can establish a very different rewrite link than the original one. It's possible. And we prove that this does not affect the replay correctness.
Are you going to define that more? We prove this does not affect replay correctness?
Yeah, the full proof is in the paper, but I probably, I can give you more information if...
Is the idea basically that it has to read the same value?
Yeah.
Even if it's from a different write?
Yeah, it returns the same value.
Okay.
Even if it's from a different write.
Okay. But if the user's debugging the code, that's still going to kind of bring... I mean, I'm just thinking about this from a practical standpoint. If they're debugging the code and they're trying to find the line in their source code that's causing the problem, if it's still going to bring them there, I consider the proof correct, right? I'm just practically. So if you tell me that's the case, I'm happy.
So if it's a failure, so this guarantees to reproduce the failure. But our focus is try to restore the exact race order so that your programmer can actually understand how that failure happened. And this, in theory, does not guarantee the original order, but give you one of the orders that can actually lead to the same failure.
Okay, so at least it gives them something to do.
Yeah, give you at least, for example, another possible order that leads to the same failure. Yeah, so it does not guarantee to give you the original order. So let me summarize that compared to leap, on this particular example, we only need to perform 4 synchronizations, and we need to log 2 actual values and 2 versions. So the big change is that so by by double logging, we do not require to synchronize, right? So we have 2 we only need 4 locks instead of 6. So this doesn't seem to be a lot of improvement compared to leap or compared to regplay. But in practice, this has a huge performance improvement. So it's very intuitive that, so what we found is that in practice, in all the benchmarks we evaluated, a large majority of the shared variable accesses are reads. So so for example, in some of the benchmarks, such as Derby, SpecGBB, more than 80% of the shared variable accesses are reads. Okay, so think about the number of, the degree of lock reduction that we can achieve using stride compared to leap. And the writes to shared variables, in our experience, are mostly already carefully protected by programmers because they are more conscious about writing to a shared variable. So our investigation reveals that, for example, in a benchmark called Derby, more than 95% of the accesses potentially incur some kind of race. However, if we only count the write race, it's only 15%, meaning many of the writes to the variables are already protected by programmer. This means that we do not need to insert additional locks for these writes. We can already leverage. So in that the performance penalty is very limited because programmer already has a lock for that writes. We can just insert instrumentation inside the lock region without inserting additional locks. Another amazing finding, probably also others have already observed the same thing, is that the context switch between those 2 double locks actually is not that frequent. So remember, we do not require a lock to synchronize those 2 reads. So in our experiments, more than 90% of the reads can be solved in the first comparison. That means there's no context switch, even if I read the value twice. There's no context switch in between. Only 58 out of 400 million reads in our experiments require 4 comparisons, which means there are 4 different versions of the value that inserted in between those 2 reads.
And those numbers are based on those specs, those
numbers based on the subjects that we evaluated. So we cannot say this could generalize to any program. But intuitively, I think it's not that surprising. Okay, so the context switch is not that frequent for the accesses. So we do log extra values. So the value logs are separate from the version log, which means that we can take advantage of the locality. So they're a long continuous array of the same value, so it's very friendly for compression. So in our experiments, we don't find we generate a lot of logs as well. So this is actually a summary of one of the evaluations we did for leap and for stride. On the left side is an array of popular Java, multi-threaded Java programs. And the second column actually shows the percentage of reads of all the traces that we collected. So a large portion of them, of these operations are reads. So that's where the technique with stride can actually help a lot. So the third column shows the overhead of leap compared to the original execution. So in some of the subjects, such as Derby, you can see that the leap already has only 10% overhead for recording. And the last column shows the overhead of a stride, and you can observe that it's significantly faster or has significantly lowered the recording overhead compared to leap. Okay. In particular, in this subject modine, leap incurs 100% 100 times overhead, where stride can really drive it down to 1.5. Okay, so this shows that to relax on the synchronization on all the reads actually has a huge performance impact on the recording overhead. So the last technique I want to talk about is called CLAP. It's a solver-based approach, which we go a step further to drive down the recording overhead. In this approach, we do not require any synchronization, okay? And we record only the branch choices. In other words, we do the path profiling. And we compute schedule by solving constraints. So this is ongoing work. I do not have full-blown detail, and our evaluation might be still premature, but the core idea is presented at the PLDI student research competition and actually won the first place. So the basic idea of CLAP is not to use any synchronization at all. So let's just record thread local paths at runtime. That's all we record is the local path. And then we can construct the execution constraints on all the shared variable computations using symbolic execution on the path. And we use SMT solvers to compute the schedule. Okay? And in more specifically, we have path constraints, we have program order constraints, partial order constraints, rewrite constraints, and we feed it to a constraint solver to compute a global order of shared variable accesses. And the good news is path profiling is pretty lightweight. It's a classic technique that people really work hard to optimize. Okay? For example, the Ball-Loris profiling is only 30%. So let me just give you some basic high-level steps of how we approach recording in CLAP. So same example, we first record all the branch decisions. Okay? So in this case, we record the branch decisions, and we collect the execution path for each thread. And next step is that we try to encode the constraints based on this path. We have different kinds of variables. We have symbolic variable for shared variables, instances for all different instances of shared variable accesses. We have a S variable that symbolically represent the value returned by remote read. And we have order variables correspond to each of the shared variable instance to represent a position in the global schedule. It's a corresponding position in the global schedule. Okay? So bottom, I'm showing how we construct the constraints. The first order constraint is just program execution order. It's very straightforward. And the rewrite constraint is basically saying that I'm trying to match the symbolic variable that represent a remote read, and I'm trying to match it with actual writes. Okay. But there are possible instances to match to. For example, this one, the one I circled, can be potentially matched to its local write or to a remote write. Okay? So it depends on the actual pairing. I can construct a different order constraint for the order variables. So if you do not bother with the detail, this basically says if that variable corresponds to the local write, the write, the program, the computation of the other thread must happen either completely before that first write, or completely after the actual read. Okay.
So in this example, I mean, the only differences in the programs that you're observing are whether or not the conditionals evaluate true or false, right?
Right.
So then you can actually have So there are certain executions in which, for example, y is equal to 1 on the right-hand side. And so you're saying by observing the control flow, you are getting constraints on the inter-thread execution, because if
So this example,
if 6 executed and then 7 executed, then you know something about y changing. And so that would require some sort of race. So on the right-hand side.
so we use the control. We use the control flow to compute. This example doesn't show that explicitly. It actually computes the constraints for each shared variable to be executed first.
But you're not
Local
I guess my point is
constraints.
You're not recording the values of variables.
Not recording.
So the problem is if you don't branch on some shared variable's value, how will you be able to reproduce the race on it?
We use, probably you can answer this better, but we use a low store.
Well, maybe I just don't understand. You do have orderings on the shared variables. Or is that what you want to compute? You don't have orderings.
So the purpose of computation is to compute values for these O's, for these orders.
Right.
To assign a global array of integers to these variables.
Right, so
all
I guess
variables.
my point is, if you just have straight line code, no conditionals, then there's only one path in each side. So what do you do in that case?
Then we don't have the path condition. We only have the order constraints and the read-write constraints here. So it's easier.
So then actually, so in that case, you basically say any interleaving is possible. Like in that case, you just observe these 2 threads executing, but but actually all interleavings are possible in that case.
No, basically, you have.
I mean, all interleavings
For
that are
example,
consistent with the values.
For example, you have a back property, right? So the schedule have to satisfy this back property. So you have another constraint here.
Right, I'm just saying that in the case where you just have straight line code with no conditionals,
Yes.
and just a bunch of assignments to shared variables and then reads, you have a lot of possible interleavings.
Right.
So
that
bug
makes
is
sense.
sort of a predicate.
Okay,
We
so
treat
you
it as
assume
a
there's some
predicate.
predicate, okay.
Some predicate. Then we
Okay.
symbolically execute that, form all the constraints, and solve
Okay,
it.
so there's at least one predicate that tells you something.
Yeah, at least one predicate.
Okay.
Yeah, that's right. So for illustrative purpose, I think this is a simplified representation of what we did, but this is the core idea is to encode different constraints symbolically. And well, on the top, I'm giving all the constraints for this particular example, and we feed it to the solver. And at the end, the solver will return an integer assignment to all the order variables that represent a position of a particular access to a shared variable in a global schedule. So this would be the order variable, and we would just use this variable and the user level scheduler to replay this program. Okay. So let me just summarize the characteristics of CLAP. So what we think the most important contribution we make is to reduce multiprocessor replay to solving 2 well-known problems. One is the thread local profiling, and the other is automatic theorem proving, which are really very developed areas or very developed techniques. And we have also a formal proof of why that replay is correct, so that the schedule computed by CLAP is guaranteed to reproduce the bug.
If the bug doesn't depend on branching, then it's not, right? For example, if you have like a null dereferencing due to data races, then since you have not recorded any like values, then I think your schedule does not say which order has been occurred. So
Well, that's a bug too.
Yeah.
I mean, that's an observable
Yeah.
bug under some semantics.
Sure.
But I mean, generally, I think you're also pushing off alias analysis to your constraint solver, right? Because in your simple case with scalars, it was great. But when you have pointers and direction, since you're not recording values, you can't use value difference to disambiguate pointers. Generally, there's a rule that if star p is not equal to star q, then p and q don't alias,
That's right,
which
that's
you
right,
can
that's-
use to your advantage when you're recording values. But you don't even have that. So you're also going to have to put all the aliasing or non-aliasing constraints
Right.
into your theorem prover too, and ask it to also resolve potential aliasing. Yeah.
Yes, that's true.
That's true. That's
so,
true.
so you're pushing off a lot. You're making your runtime cheap, but you're pushing a lot of problems onto the theorem prover, which is not bad. But I just sort of wonder. I mean, it's not just about the. You're going to have some memory model, right, to reason about aliasing. Because, like in his case, like you may or may not get the error, depending on whether some alias occurred or didn't occur earlier.
Yeah, the aliasing is definitely a problem, and I think CLE gives us a lot of symbolic representation of the pointer values, but there are also some problems with arrays, stuff like that, and yeah, that we admit it's a problem for us too. By including those having those order variable, another advantage of our approach is that we can represent different relaxed memory models very easily. For example, TSO, PSO models, and we just encode a different order constraints into our constraint solver to be able to address the bugs in these relaxed memory models. Another interesting characteristic is that, same as the work of chess, we can encode to bound the search or bound to give easier time for the constraint solver. We use a context switch bound, preemption bound, to reduce the search space. Basically, we can provide a constraint on the sum of the delta of the thread local consecutive order variables, so that we can sum them and put that as a constraint into the constraint solver, so that we can ask the constraint solver only to give us a schedule within a certain number of preemption bounds. So this is another way for us to be able to make computation tractable. This is a preliminary evaluation result for CLAP, and these are some of the subjects that we used. And the CLAP is completely implemented on LLVM, so on C programs, different from my earlier subjects. Okay, so it's all on C programs. What we observe is that the recording overhead ranges from 10% to around 269%. So we also implement for evaluation purposes, a version of Leap on LLVM as well. And we observe some significant reduction, which is as expected. All right, so I guess let me just make some conclusions. I hope I sort of highlight the challenges of user-level deterministic replay. Is that we want to reduce the recording overhead. We want to avoid some Heisenberg effect, where the instrumentation makes certain type of bug disappear. We want to also reduce replay complexity, although in this talk I didn't have time to talk about. And I presented 3 techniques: Leap, Stride, and Clap. And in the future work, we'd like to focus on things like event-driven programs. We very much want to address how to replay long-running systems, and also how to distribute a bug in the distributed systems. Okay, so thank you very much, and thanks a lot for your time and attention. For more information about our research, this is my homepage, and maybe I think I took a little bit long, but
Thank you very much.
maybe some feedbacks and suggestions.
So I'm curious about your plans for future work. Can you say a little bit more about what you're planning to do with event-driven programs? I mean, what kind of programs are you referring to when you say event-driven programs?
So, I think about 2 types of event-driven programs. One is the low-level event-driven programs. The most famous one is the Linux kernel, things like that. And For my background, I'm more interested in addressing event-driven middleware systems, for example, or these messaging systems, where debugging them is very, very difficult. So I have some preliminary ideas, but my surprise is that there's maybe, I don't know yet, but I don't know of any replay work that address this kind of system. So that's why I think it's worth investigating.
I think that one challenge here, I've sometimes thought about this problem, is that when we started looking at multi-threaded systems, there were standard libraries that programmers could use to express multi-threaded computation. So in the open source world, in the Unix world, we had this pthreads.
Right.
On Windows, there is the Win32 library, and Java and C#, they all have these standard APIs. But with these in this event-driven world, it seems to me that there's just a huge variety of primitives and libraries. So it's kind of hard to imagine which one should you target. You see what I'm saying?
Well, we start with well, I think the world is not completely chaotic.
No.
For example, there are also well-defined type systems, type-based messaging, so that we can have some kind of information about the semantics of the messages. It's not, and there's also standards like Java messaging system. It's a standard. So I think we have some ground to start. It's not really completely chaotic.
Okay.
But unfortunately, I don't have further experience in that. I just feel it's a great need to have that.
Yeah, I agree with that.
Yeah.
I think you have not shared the actual analysis time for the offline one. How was that? I mean, was it really scalable to solve the schedule problems?
So the complexity is the same as chess. It's exponential to the number of threads.
Yeah, so
to enumerate.
Yeah, I can understand the complexity in a theory sense, but I'm just asking, in your practice, can really re-execute, replay the record execution in a reasonable amount of time?
Yeah, for all these subjects I list here, we can actually, so I think I want to race against the time, so I didn't explain it. So the second column is actually the time taken to reproduce to trigger the error for these subjects.
Including the offline analysis.
No.
No, this is only reporting the runtime overhead.
Right? Yeah, just. Yeah.
And the time taken, we have a table, but I should put it on a backup slide.
Yeah, basically for the first first 6 programs, we finish it within 1 hour. And for the last one, it's
That is the benchmark.
What are the last ones? They run overnight? Or?
it's a little bit difficult because there are too many context switches need to explore.
That is really a special benchmark that
That's all it does?
Yeah, all it does, and it's just kind of like a stress testing whether a replay system actually works or not.
Which one is that?
That is RACI.
The last one, it's
the worst one.
It's
Hand to
basically
practice
race all the time.
I see.
So for that, I think it's a special. Well, that's the only benchmark that we are unable to produce a schedule. But hopefully, in real-world programs, none of the race condition is like that.
It's not a real application.
So all these subjects are small, but they are carefully constructed to produce a concurrency error. So in terms of replay difficulty, I don't think they're more easier than the real or larger benchmarks, but we're still working on larger benchmarks.
You said you're using CLE, right?
Yeah.
So you're actually using CLE then to do exhaustive enumeration to find the path? So you're not really truly doing symbolic...
We modify CLE not to duplicate the states. Because we have the path, we just use it as an engine to give us the constraints along the path.
Right. So you're using CLE to give you the intra-thread path constraints.
Yeah.
But then to that, you have to add all these other constraints.
Right.
Right. So then those are being added in.
Right.
I see. So you're gonna let CLE execute to some point, or you just, I don't quite understand. So are you gonna just take okay, you have the separate thread traces, you're just gonna make one pass with CLE on each to get a formula per thread?
Right.
And then you make one big call to the solver, or?
So basically, after we collect the path constraints for each thread,
Right.
and then we conjunction them, and then we encode all the other execution constraints.
So there's one big call.
There's going to be one big
There's
call.
one big call, right? Okay. And that call, if it comes back, will give you a model for the ordered variables.
Right.
That's interesting. So that trace then, so unlike a typical use of CLE or Sage is that you go until the first branch and then you say, can I go a different way? You're not using it
We're
this
not
way.
using that.
Right,
You say I have
you're
a
just using it for the
long
path
execution
constraint.
and I just want the path constraint
That's
for the
right.
That's
whole
That's
thing.
right.
And furthermore, that's why you get into this issue of symbolic pointers too, because CLE is not doing everything symbolically, and you would like it to make more things symbolic, probably. Is that true?
So basically, we need to mark the shared data nodes, the loads, to be symbolic.
Right, because CLE is, I mean, as I understand it with Sage, you sort of mark some bit of state as symbolic. Is that correct? But then there's all this other stuff that you want actually to be symbolic, that if CLE were just to treat it its default way, it would not be symbolic. It would become,
Because of the interference, you mean?
because it would be
No.
concrete.
Yeah, we have to address the symbolic address problem.
So you need to make more things symbolic. CLE is essentially, like Sage, it's trying to find changes to the input byte stream that will cause the sequential program to go a different way, right? But in their case, they have all these global memory accesses whose, like for a single thread, it's just like a function of
So
the
this
thread.
basically this extra data, because they're analyzing each thread separately, there's this extra data that
They
is
wanna
coming
make
in
symbolic.
Yeah, okay.
Is that correct? Is that?
Because it has its own symbolic memory representation,
Yeah.
and then
Yeah.
it actually emulates the sort of the memory assignments
Yeah, that's right.
as well. So
Huh.
it gives us some kind of alias information, but not for all the variables.
Yeah, so this
It
is
doesn't-
quite interesting.
Yeah, it doesn't solve arrays,
Yeah.
for example.
You definitely want to do you definitely want to do reduction on this trace so that you don't look at all the possible
So
points for preemption.
There's the research group at NEC Labs.
Yeah.
They do stuff like this, right?
Yeah, I was telling them about
Like Malay Ganai.
Yeah, Chao Wang.
but it's
And
different.
Chao Wang, yeah.
But it's
Yeah,
different. They don't have this local. They're doing something different because of the local stuff. Generally, there what happens is you record a partial order of a parallel execution, and then you search for other schedules that obey the same constraints, but might find a bug,
I see.
right?
Okay. No, so yeah, this is different.
It's
yeah.
different. It's different. Yeah, it's a different take.
Definitely a lot of room for optimization, but the key idea is to pass profiling and then do symbolic execution on that pass and solve the constraints.
Yeah,
And
you can call it path profiling, though. I mean, you're really doing a full instruction trace.
well,
Right?
pass.
I mean,
Recording
paths
of the
are-
path
I know
decisions.
the path decisions, right? But it's I would talk about instruction traces, but yeah. Okay, cool. Well, thanks again.
Thanks a lot. Thank you.